All right. So again, project 2 is due now, but if you need another hour or something, just hang on to it. Give it to me later today. I'll be in this room this afternoon, so just come on by, even if we're in the middle of class, and give it to me. You could also put it underneath my office door. Project 3 is officially assigned. It is due on the 22nd, which I guess is a week from Wednesday. Okay. That's that. And so between, let's see, and then on the 17th, what day is the 17th? Is that Friday? Friday is our third quiz. It is on 3 classes of material. And then at the end of this week, we will have finished the new material for the test. Wednesday of next week, remember Monday is President's Day, there's no classes. Wednesday of next week is our review day, and then Friday is our first test. Any questions on any of this? Stephen? Do you have our last quizzes? I do. I'll give you the quizzes today. Yep. So one thing, thank you for mentioning that. Any other questions on the calendar? So one thing I wanted to mention about the quizzes is that I think they went pretty well. I have them and I'll give them back shortly. But one question that kind of stumped a lot of people that I was surprised by was number 2. It says here, I'll make this a little bit bigger. All right, a credit card balance accumulates interest at a nominal rate of 18% per year, compounded continuously, and then we want to figure out the effective annual rate, meaning something you could type into the calculator. Is it going to be more or less than 18%, like the real rate? It's more, because we're compounding continuously. So it's 18% on the surface, but it's really going to end up being more than that. So so if you wanted to kind of figure stuff out, like a lot of folks said, okay, I know I'm going to use a PERT type formula. Sometimes I can write on Word, and apparently today I can't. So let's just go back to something I can write on. So if we're doing an 18% thing, then we know we can use PERT because it's continuous compounding. And you know, we can just pretend it's like a $1 that we start with, and the interest rate was how much? Was 18%, so 0.18. And then how much time is going to elapse? Is 1 year. We want to figure out what the annual interest rate is in reality. So you can type that into the calculator. It's going to give you what your dollar has grown to, right? So what would you do to this thing to find out what the actual interest? You got to subtract off your dollar, yes? So so then subtract 1. So e to the 0.18 minus 1. This was the effective interest rate. I noticed that the homework we did was this kind of a question? Okay, I can change that. Thank you for the observation. Like I said, the textbook changed, the edition changed, and so I'm certain that I put some problems in the wrong section, and I'm certain there's some wrong page numbers in there you guys will help me find, just like that one. But I do know that we wrote a formula that basically said, you know, the effective rate is e to the r minus 1, and I don't know how readily we can find it, but I mean, it's in the notes someplace before. Did we do it somewhere here? I don't know. I don't want to take our time trying to find it, but it's in here someplace where we just put e to the r minus 1. And so either you know, like, be comfortable enough with the PERT thing to be able to figure out, you know, how would I find the true interest rate, or you know, you have that index card, and so just write down all these different versions of these formulas on the index card so you can refer to them. My goal is not to have you memorize e to the r minus 1. I've memorized it, but that's just me, and I don't expect you to memorize it. Anyway, so use the index card. There's lots of formulas floating around. All right, so we're on page 33, and we'll do a little bit of history here. Oh, by the way, I think some groups finished this big baby thing, but other groups didn't quite get there. Anybody remember what the answer was? It was about 33 years, I think. How long until Connor becomes more massive than the Earth was about 33 years, assuming he doubles every 5 months. Oh, and Stephen, you and I talked about an alternate method you had, and I figured out what was happening with that. So let's chat right after class. Okay. Okay, so here on page 33, we have number 1, and we can begin with Topher. Raise your hand if you have a slide rule. I have one. I'm quite happy to have one. Right? Raise your hand if you have ever touched a slide rule. Right? A few more. I've heard of a slide rule. Right, but if you go back 30 years, you know, we don't have or 40 years, we don't have these nice handheld calculators, and we have slide rule. That's how we do all the calculations 40 years ago. And so this is a fairly recent thing. This, you know, the advent of the technology that we have in our pockets, we take it for granted now because it's all that most of us have ever known. But, you know, talk to your parents and ask them, and they will say, oh yeah, we did all kinds of stuff with slide rules. That's what we had before the calculator. Used to be that in the back of every algebra book was a logarithmic table. Go to the back of the algebra book now, it won't be there. We don't need it anymore because we have the calculator. Napier, the same guy who invented logs, also popularized the use of the decimal point, a handy little thing that didn't exist all the time. And here's an anecdote. We'll get Kelsey to read the anecdote. You understand? It could be. You understand the cleverness of this guy who invented logs? He said, I have this magic rooster. He's going to catch the thief. Just touch him on the back and he'll know who you are. But he put this black stuff that would come off on the people's hands. It was kind of a dark room, and he coated it in this black stuff. And so the one guy who actually was stealing was afraid to touch the magic rooster. So he went into the room and pretended to touch the magic rooster, but didn't. And he came out. And you know, like, what's the phrase? To be caught red-handed? Right, so this guy was caught like regular handed, like he was, because his hands weren't black, he was identified as being the criminal. Oh. All right, we'll go to number 2, Chris.
Let's have a look at the graphs common in that logarithm.
All right, so the two graphs look quite similar. First step is to figure out which one is the graph of ln of x and which one is the graph of log x. And so, for example, if you plug into this guy right here, if you plug in x equals, let's say you plug in x equals 1, how much is the log of 1? Is 0. So do you guys buy that, like if you plug in x equals 1, the y value is 0, log of 1 is 0? Okay, so 1 comma 0 is on log of x. Oh look, 1 comma 0 is right there. So that one is log x, right? Yeah. Yeah, if you plug, it doesn't matter what you plug, what log it is. If you plug in 1, you're always going to get 0. All right, so we need more information. So the more information is this. If you plug into this guy right here, 10 for x, what is log of 10? Log of 10 is 1. So the point 10 comma 1 is on one of these curves. 10, 1, it's not on that one. It must be this guy right here, 10, 1, which makes this guy, f of x is log x. What's the point that's like 10, 1, but on this curve? Is e comma 1, right? If you plug in e, you should get e, and then ln of e is 1. And so the point e is around 2.7, and look, there it is. This is e comma 1, which makes this one the ln function. So the graphs are quite similar. If I just asked you to sketch ln of x and you drew one or the other, I'd give you full credit, right? I mean, they're pretty much the same graph. The log graph, first one, grows a little bit more slowly than the ln one does, but they have a lot of commonalities. So let's go to 3. Allie. Okay, so yeah, so let's start filling in some stuff here. So what's the domain, which is the set of x's? Everything bigger than 0. Notice that you can't plug 0 in. It never hits the y-axis. And you can't plug negatives in. So the domain is all the x's bigger than 0. The range is all real numbers. It goes down to minus infinity, goes up to positive infinity. It takes really long to get up to positive infinity. It grows really slowly. but the range is all real numbers. Where are these functions increasing and where are they decreasing? Yeah, they're always increasing, right? They never turn around. There's no maximum, no turning points. So increasing on 0 to infinity. Same as the domain. Are these graphs concave up or concave down? Down, right? If you were cups, the water would fall out. Concave up things look like upwards cups. So concave down. And you give the same thing. You tell the x values for concavity. We don't care about the y's, only x's. And then finally, end behavior. As you go to the far right, run to the right forever, what happens to the y values? They get bigger and bigger and bigger. It looks like they're leveling off. They aren't. They get bigger as high as you want it to be. It will be there. It's just going to take an awful long time to get there. So you can say the limit as x goes to, how do we say go to the right forever? Infinity of f of x. That's our way of saying we're going to describe the y values. And what happens to those y values? They get infinitely big. So that's equal to infinity. Why doesn't it make sense to do the limit as x goes to negative infinity? There's no graph out there, right? So we don't even put the other one. And then finally, the vertical asymptote, what is it? It's x equals 0, right? It's the y-axis. And so we can just say x equals 0 or the y-axis. That's the vertical asymptote. It's very close to, but never touches. And I just want to say one thing to impress upon you how slowly these things grow. At the end of this first graph, how high was my function? It was up at 1, right? So like to get up to 1, I had to run all the way, whoops, that's not what I wanted. To get up to 1, I had to run all the way out to 10, right? Went to 10, up 1. What if I wanted to get up 2? Get out to 100 because the log of 100 is 2. So we'd have to go all the way out to 100. So we're out here. That's 20, 30, 40. So maybe just the other side of this wall. And how high is the curve? Is it 2? If I wanted to get to 3,000. All right, let me get my orientation here. So where's the east building? East building is that way. So what's over here? Is there fields? More fields. All right, so we go out to 1,000. Right? The other side of this wall is 100. You go to 1,000, and how high is the graph? 3. Get to downtown Greenfield, maybe we're up at 4. Keep heading this direction. What do we say again? East, south? Head south? I thought east was over that way. Oh, north is this way. Okay, at least I had either north or south. Okay, so we head north. So maybe we get to Canada, and the graph is at 5. We get to the North Pole, we're up at 6. We leave the Earth's atmosphere, we get up to 7, right? It gets there, but it gets there really, really slowly. As high as you want it to be, it will get there. But it's going to take a long time. All right, number 4. Where are we now? We'll go to Melissa. Differ by. Yeah, okay, so there's a lot of words in there. I don't expect that sentence made sense yet. Let's do an example. We'll go to Steve in the back. 5. Okay, so center of the Milky Way to Earth, 26,000 light years. Andromeda Galaxy, quite a bit further, but I don't have a good sense. Like, how does 2.5 million compare to 26,000? These numbers are both too big for me to grasp. So let's divide them. 2.5 million divided by the 26,000. And whatever we get, that's how many times further the one thing is than the other. So what do we get here? So we'll say about 96.2. So what does it mean? It means that the Andromeda Galaxy is about 96 times as far from Earth as the Milky Way is, right? So like if the Earth is here where I am, and Bryce right here is where the Milky Way is, then how do I find the Andromeda Galaxy? I'm going to go like 96 times. I'm just going to keep walking, but 96 times the distance between me and Bryce, right? Okay, so that gives me a good sense. These numbers are way too big for me to understand, but at least I can say, well, if I'm here and you're there, I just go 96 and then I'll find the next thing. Fair enough. Okay, now let's talk about this business about order of magnitudes. So as Melissa read, it says order of magnitude is a power of 10, and the log of the ratio of two quantities, this is the ratio of two quantities, the log of the ratio of two quantities is the number of order of magnitudes they differ by. Let's pause before we hit that log button. Roughly, what power of 10 is this? Just count the number of digits. But there's 7 digits in there? So it's something on the order of 10 to the 7, yes? It's a little less than 10 to the 7, but it's more than 10 to the 6th. What about this number right here? Count the number of digits. That's like a 10 to the 5th. It's less, but it's close enough. Okay, so then how many, so this is of order 10 to the 7th, and that's 10 to the 5th. So how many more digits did we need in the top one? We needed 2. All right, now what I want us to do, so then, like 2 more digits is what we needed to make the top number. Now I want you to take the log of this 96.2. What do we get? 1.98. Very close to what number? 2. That's what we're doing. We're saying if you want to know how many more digits you need, you take the ratio and then you take the log. That's how many more digits you need. You can. The reason we don't just look at how many more digits is that how many more digits is not as precise as we're interested in. We're interested in something like it's 96 times as big. It's almost 2 full orders of magnitude, as opposed to being like 1.5 orders of magnitude. Yeah. So this is our precise way of really saying, how many more digits do we need? Okay, let's go to the next page. I missed something. What did I miss? Not the next page, number 6. And I think we're up to Todd in the back. Okay, so there's a lot of chemistry there, and I suspect some of you guys know more chemistry than others, and that's fine. Suffice it to say, I'm just trying to show you an example where a log function is appropriate outside of a math class, and it turns out that the acidity of some substance is measured with a log. You take the hydrogen ion concentration, whatever that is, in moles per liter, whatever those units are, you take the log of that number, you put a negative in the front, and you get something called pH. So my chemists in the room, what's the smallest and biggest values of pH? 14 is the biggest. And is it 0? Is it 1? 1 to 14. Yeah. This is 0 to 14. Okay, so 0 to 14 is this pH scale, whatever it is. The number right in the middle is 7. That's not acidic, or what's the opposite of, or basic. What do we put there? What has a pH of 7? Water. Okay, so something neutral, water. I learned very recently that rainwater is not neutral. It's acidic. I had no idea. And now I desperately run fast when I'm in the rain. I'm just kidding. Now that I'm aware, see, knowledge is a scary thing. Okay, so let's see if we can use this formula even if we don't understand all the chemistry. We'll go to part A for Sam. Okay, so let's plug into our formula here. pH equals negative log of H plus. H plus is this 0.1 number right here. Can you guys find this without a calculator? Talk to your neighbor and see if you can figure out the value of this without a calculator. So what is log of 0.1? It's negative 1. 0.1 is a tenth. It's 10 to the negative 1. So what is the pH of battery acid? 1. Remember, the pH scale is between 0 and 14, with 7 being neutral. Battery acid, would you guess it's acidic or basic? It is acidic. Okay, so apparently the acidic things are on the small side of the scale. 0 to 7. The acids, 7 to 14 are the bases. Let's try the next page. And we'll do B. I think we're at Emily. All right, so in this case, we're trying to find the H plus, but we know the pH. I'll put the formula here again. Negative log H plus. So where does the 12.5 go? It's in the pH. 12.5 equals negative log of something. See if you guys can check with your neighbors and find the H plus. So anybody have a number for me? I didn't get them all, did I? Tell me, where am I wrong? 1622. Okay, we'll just see. We'll just do that. Okay, so all right, so that's the hydrogen ion concentration, whatever it means. Now, 3 times 10 to the negative 13. Is that a big number or a small number? It's ridiculously small, right? It's very close to what number? 0. It's really close to 0. Super. So bleach has that concentration of hydrogen ions. Battery acid has a 0.1. This was acidic. What did we find out about bleach with a 12.5? It's very basic. So we've got almost 2 extremes here. We have something close to 0 and something close to 14. But the difference between them, well, let's see. So this had a concentration of 0.1, which I would say is pretty close to 0. And the other one had one that's so close to 0, I can't even distinguish it from 0. So all of the action that distinguishes whether something is a real acid, like battery acid, or a real base, like bleach, happens between roughly 0.1 and 10 to the negative 13. How much space is in there? Hardly any, right? I mean, like, it's all happening in this tiny, tiny, tiny little interval, which is why we convert. This is why we use logs here, is that all the action is happening in this tiny space between 0 and 0.1. And it's so hard to kind of like tell what's happening just looking at 10 to the negative 13 versus 10 to the negative 7. I'd call them both 0. You take logs, and now all of a sudden we have numbers that are manageable. There's nothing like about chemistry that says that pH has to be defined in terms of logs. We put logs here to make these numbers user-friendly, right? We talk about things being user-friendly. That is why we use logs here. 10 to the minus 13 is not user-friendly. Neither is 10 to the minus 7. But those numbers are quite different. And so we hit it with a log to give us numbers between 0 and 14. We can deal with those. Todd.
I noticed that all you did with the 12.5 is make it negative.
Yes. Yep, that's how pH works. Yep. Take the pH, make it negative, and put it in the exponent of the 10. Good. All right, let's try C. Tacitae. Oh, question.
Just to go over how that equation happens there.
Oh, which one? The 10 to the minus 12.5? Oh, yes, absolutely. So So first thing I did is I took that negative sign and moved it over there, so it's just negative 12.5. And then the definition of log, remember there's an invisible 10, oops, there's an invisible 10 sitting there, 10, no. And we know that the definition of log is 10 to that number equals the h plus, right? That's like our pattern for logs. So 10 to the negative 12.5 equals h plus. That's it. That's it. Okay. Which one? The circle? So if I want to focus everybody's attention, I say, everybody look right there. Okay. All right. There's another one that it sometimes works for me and sometimes it doesn't. There, it didn't. I don't know. It's supposed to be doing something which it isn't. There we go. Yeah. All right. Okay. We are on C. Emily, did you read? No. Yes, you did. Pass a day. Okay, let's see if we can start thinking about picking apart that formula. We're imagining a 1 order of magnitude increase. Orders of magnitude are powers of what number? 10. That's what an order of magnitude is. So if you have something which is called H plus, and let's just say that's the given liquid, and you increase the H plus by an order of magnitude, it means you're making it 10 times as big. So let's make it 10 times as big. Right? It used to be H plus, now it's 10 times H plus. The question is, what happens on my 0 to 14 scale? What it used to be compared to what it is now? So here's where we come up with some of our properties of logs. Negative. This is log of a product, right? What can you do with to separate a product? It becomes a plus. So that's log of 10 plus log of H plus. And how much is the log of 10? Is 1. This is negative 1 plus log of, oopsies, negative 1 plus log of H plus. It will be. Right, so it's negative and then 1 plus log of H plus. And then as Topher points out, we can distribute, and I don't have any more space, so apologies for going here. Negative 1 plus log of H plus. Nice. Thank you. Okay. So it used to be negative log of H plus. That was the start. Then we made it a 10 times H plus. Well, there's my negative H plus, negative log of H plus that we had before, right? This thing, without the 10, is the same as this thing, yes? So what it used to be, it still is. But now what is it? It's 1 less than it used to be. It used to be that, now it's 1 less. So if you increase the hydrogen ion concentration by multiplying it by 10, what happens on this 0 to 14 scale? You go down 1. Increase the concentration by a factor of 10, you go down 1 on the scale. If we had bleach at a 12.5 and we made it 10 times as this hydrogen ion concentration, what's the new pH? It goes 11.5. That's what it does. All right. Let's try 7. Kate. Okay, let's pause right there for a second. This is the same idea as the pH example. All of the action for pH was involved with these numbers that are tiny, 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 all very close to 0. And so we hit them with a log to pull them apart. Same idea here. We can hear, like if you're like a sound of a pin drop, it's on the order of about 10 to the minus 16 watts per square centimeter. Whatever those units are, that's how, like the quietest sound that you can hear. And then things get louder than that. But things get really like much louder than a pin drop, right? But still, that number is going to be really close to 0. And so instead of dealing with 10 to the minus 16 compared to the 10 to the minus 8, We're going to use logs to try to pull these things apart, get us some nice number. Do you know what unit we use to measure sound, really? Is decibels. So let's talk about decibels. We'll go to Richard. Okay, thank you. We'll go to Hillary for 8. Okay, so we've got these two numbers. 140 is quite loud. 110 is still very, very loud. Turns out a conversation is probably around 50 to 60 decibels. In terms of the intensity of the sound, all of these things have intensity very close to 0. Maybe 10 to the minus 12, 10 to the minus 8, like really, really tiny in terms of how we measure the intensity. But we can't deal with those numbers, so we make friendlier numbers. And that's this whole idea of the decibel scale. So let's go to 9, Vance. Okay, so let's give this a shot. So here's the magic formula. So we're going to say the starting value, or the initial decibel rating, is going to be 10 log of I over I0. That's some starting sound with an intensity of I. And then we're going to make it triple. So the triple version is the same, 10 log I over I0. But the thing that has tripled is the intensity. So it used to be I was the intensity. What's the new intensity? 3I. That is how we triple the intensity. Everything else in the formula stays the same. Intensity is the only variable. So first, are we okay with the setup? You got some starting sound with an intensity of I, just calling it something general, I. Then you triple the intensity, and the question is, how do these decibel rankings compare? I expect that the triple sound has a higher decibel rating. Is the higher decibel rating going to be 3 times what it used to be? Is it going to be up by 5 from what it used to be? Is it up by 3 from what it used to be? That's what we're after. Tripling the sound, what effect does it have on the decibel rating? All right, same idea as before. We need to use our properties of logs. 10, oops. 10, okay, I'm going to keep that 10 there, and let's deal with this log business. I've got a product. I've also got a quotient. Couldn't I make it sums and differences? Again, right, products become sums, quotients become differences, but that's not really what I'm after. Do you guys see that I'd really like to keep something the same? I want to eventually compare to my original, right? I really like it to be I over I0, so I'm going to force this. I'm going to make a decision to not split it up in any old way. I'm going to split it up so that it's recognizable, so that it's something that looks like it used to. Well, if I split off that part, then what's still over here is the 3. I think it's just a 3. 3, so if you multiply the 3 times this other fraction, it's exactly what we had. You have to think to make sure you recognize like how to split it, because there were other ways to split it, but I think this is the way that's going to be fruitful. Other questions on splitting it this way, like why we did it or how we did it? Todd. I don't know what we did last semester. I can barely remember Friday. What do you? Can anybody from our class last semester, did we do? Yeah. I don't know if we did exactly this kind of a thing. Yeah. Okay, and then I think we can just distribute the 10. So we get 10 log of 3 plus 10 log I over I0. And now we should be happy. In addition to being in a pre-calculus class, like, do we need any more than that to be happy? What do we see? Yes, we got 10 log 3, and then what about the rest of this? This is what we started with. The goal is to make it look like it started. So it looks like it started plus this additional thing, which turns out to be 10 log of 3. So you can type 10 log of 3 on the calculator. What do we get? 0.477. 4 points. Okay, then times the 10. Okay, 4.77 times the 10. So if you triple a sound, what happens to its decibel ranking? It goes up by 4.77. That's what it does. Whether you're tripling the sound of a pin dropping or whether you're listening to 3 rock concerts simultaneously, whatever the original rating of the thing was, add 4.77. That's the new decibel rating. Any questions on that? What's that? It's something that is triple in terms of the intensity of the sound. Yes. Other questions?
Having the jet aircraft is like 18 times
Okay, Garrett is asking a good question here. Garrett wants to know, how do these things compare? You have a jet, and you have a chainsaw, and the numbers are 140 and 110. Can you guys work with your neighbors right now? We'll spend a couple of minutes answering Garrett's question. How much more intense is the 140 decibel ranking than the 110 decibel ranking? I think it's more than 19 times. All right, so some groups have tackled Garrett's question. This 140 and this 110, they differ by 30, yes? And we have this random fact about if you differ by 4.77, then you are triple as intense. So we can use that random fact. So maybe we can take 30 and see how many 4.77s we can squeeze in, how many triplings we can squeeze in. And that's around 6.3? 6.3. So 6.3 triplings. And it's very, very tempting to multiply and get 18 times as intense. But that's not right. If you triple twice, what have you really done? You multiply by 9. If you triple a third time, you're multiplied by 27. We are tripling 6 times. So that feels like an exponent to me. What to the what? 3 to the 6.3. Say again? So say about 1,002. So a jet aircraft is 1,000 times as intense as the sound of a chainsaw. That's what this says.
You gotta make your head explode though. Chainsaws are loud.
Chainsaws are pretty loud. Yeah.
Is there any way to figure that out? Just using a lot,
Yeah. So, okay, so a couple of things here. First, I don't know that I have ever been within 50 meters of a jet aircraft flying in the air. So like I can't even know. Like I think planes are loud when I'm close, but am I within 50 meters of a flying plane? I don't know if I've ever been that close, you know? So it's loud. And so then, could we do it without this? Because this was a random fact that we had just established, that 4.77. So if you want to try without, here's another option. Okay, so we know that they differ by 30. That part is, well, in fact, why don't we change it real quick? This times 10 business is, again, just to try to make it user-friendly. The times 10 in the front, where is it here? Like that times 10, just trying to make it user-friendly. So what if we divide them by 10 just to really get our hands on the logs, okay? All right, so let's divide both of these guys by 10. And the 140 turns into a 14, and the 110 turns into an 11. And so really, how much do they differ by? They really differ by 3. Differ by 3. But this is a log, right? What's the base of the log? It's 10. And then 10 to the 3 is the 1,000. Right. I didn't say we should use the 4.77. It's about a,
That's a little bit.
that's what they did. I didn't. We did. Okay. So here's what. That's a good question. Thank you for asking. So here's what we are going to do. There's this scaling sound activity, and we have 25 minutes. I don't know how long this activity will take. So get through it, and if there's time, we can maybe start next class. I don't know, but I will say this. The point of this activity is to kind of help you develop some more intuition about these logs, and you know, and we're going to use sound to try to help develop that intuition. I will say some of the questions on the next page are rather straightforward calculation type things. Others are designed to stretch you a little bit. So if you feel your head kind of pushing back, that's part of the goal of this activity. Okay. Some of these questions are designed to push you. So take a look at the reading there, and then on the next page, work through the questions. There is an answer key, and check with each other along the way.